Hello, everyone. My name is Yongkuk Jeong, and I'm an assistant professor at the Department of Sustainable Production Development at the KTH Royal Institute of Technology in Sweden.
Hello, everyone. This is Tarun Kumar Agrawal. I'm a postdoc researcher in the same department as Jeong.
My name is Erik Flores-García. I am a postdoc at the same department as my two colleagues. And today we're very pleased to be transmitting virtually from Greece and presenting our study, which we've titled A Reinforcement Learning Model for Material Handling Task, Assignment, and Route Planning in Dynamic Production Logistics Environment.
Why is this topic important? It is a good question. I would like to begin this presentation by highlighting the importance of production logistics for the manufacturing industry. Production logistics is an essential support function for manufacturing and involves all activities and processes connected with managing the flow of materials and information within the physical limits of an isolated facility. You may be surprised to know that according to recent studies, nearly 95% of the activity that takes place in a factory deals with moving materials. For example, assemblies, waste, packaging, spare parts, or brand new products. More importantly, production logistics accounts for up to 50% of the total manufacturing cost of an item, 25% of employees, 55% of the space, and 87% of factory time. Needless to say, manufacturers around the world realize that for factories to remain competitive, it is crucial to move materials to the right place at the right time, with the right quality and at the right cost. Recent studies suggest that ad hoc practices in production logistics are no longer sufficient to grant a competitive advantage. Therefore, researchers propose a shift to smart production logistics, involving the use of digital technologies, including cyber-physical systems and Internet of Things, for making machines and material handling equipment smart. Smart production logistics facilitates the real-time perception and response and autonomous decision-making in many aspects of logistics, including material handling.
Similarly, when we discuss production logistic environment, especially routing of material handling, it requires addressing dynamic aspects, including the rapid changeover of circumstances in the modern factories, interruptions, timely response to variations, and traffic of material resources. In this direction, smart production logistics benefits routing of material handling by reducing the make span and thus increasing the efficiency, reducing the energy consumption, and also helping in on-time delivery. Similarly, when we talk about traditional route optimization algorithm, they are mostly inefficient in case of rapid variation or changeover, in case of interruption due to traffic or other conditions, and they mostly follow a static route which is based on a predefined condition, and thus most of them uses high amount of resources. In this direction, for a smart logistic process, modern artificial intelligence-based tools can be helpful for designing dynamic optimization of routes that can reduce time, increase efficiency, and discover new potential routes.
Recent studies propose applying reinforcement learning for routing of automated guided vehicles and robots for material handling, including dynamic aspects. Reinforcement learning is a method including agents that learn behaviors by trial and error for maximizing a cumulative reward and interact with, rather than depend on, complete models of their environment. Research argues that applying reinforcement learning to routing of material handling may present two benefits. First, improving route generation and system response time. Second, agents learn, adapt, and optimize according to situations that arise from the dynamics of factory floors. Recent studies provide a precedent of reinforcement learning for supporting the dynamic of scheduling and path planning in the field of production logistics. First, in relation to scheduling, recent studies delve into dynamic scheduling using multi-agent reinforcement learning, formulate schedules for complex job shops as Markov decision processes, or apply reinforcement learning to warehouse management. In relation to path planning, recent publications compare the results of applying reinforcement learning with existing heuristic algorithms and using human expert knowledge as input. Route planning of online robots and hierarchical structure for long-distance route search. Optimal route search for multiple robots in dynamic environments. Or route guidance for Fab Lab overhead hoists.
But still, it is not easy to find practical applications using reinforcement learning in the manufacturing field. Why? Here are some reasons. First, machine learning algorithm can be failed for various reasons. Sometimes there is not enough data to train the model, and sometimes the model or algorithm is not mature enough. The reinforcement learning is slightly different from the other machine learning method. Unlike supervised learning and unsupervised learning, the reinforcement learning method can train a model even in the absence of data. However, when the problem is complex, it requires a lot of resource to train, and the trained model does not necessarily guarantee an optimal solution. Therefore, we would like to propose a reinforcement learning architecture applicable to dynamic environments such as smart production logistics. The architecture we propose basically includes the basic component necessary for reinforcement learning such as state, reward, environment, and action. In addition, it includes rules, practical knowledge, and logistics environment that can define the production logistics system. AGV currently uses its own algorithm to navigate a path and can detect obstacles through its own cameras and sensors. At this moment, if an obstacle is suddenly detected, the route to the destination is researched from the stopped state. However, if the reinforcement learning model is used, the optimal route can be continuously improved by periodically calling the route finding model. In other words, the existing AGV path searching method in a dynamic environment wastes the time recalculating the path. But the method using the reinforcement learning model can save this time. Of course, how often to call the model and how to set the minimum safety distance to the obstacle to prevent collision can be set separately. Next, we define the logistics environment. The general manufacturing material handling environment can be conceptually defined as shown in this figure. There are several stations that perform the production processes, and the production logistics environment is defined around these stations. We have implemented this conceptual model as a digital twin, and it can be used to verify and improve the result of future reinforcement learning models. A production logistics environment can be defined with static dynamic obstacles, delivery points, and AGVs, as you can see in this diagram. To apply this environment to the reinforcement learning model, it is simplified using grid. There is the agent, which is the core of the reinforcement learning model. We define two agents, one for assigning tasks and one for the planning routes. The task assignment agent plays the role of allocating the defined logistics task to the AGV based on the production schedule. As shown in this figure, after production tasks are completed, the product or the part must be transported to the next station where logistics tasks are defined. This agent identifies idle AGVs and allocates logistics tasks. The routing planning agent plans the route so that the AGV assigned logistics tasks can move to the destination avoiding obstacles. Through training, it is possible to search for a path that is close to the shortest path. To define the reinforcement learning model, action, state, reward must be defined. Here is an explanation of the action. The task agent assigns the task to the idle AGV as mentioned before, and the route planning agent allows the AGV to move to an unoccupied cell. At this time, the options that can be selected are up, down, left, right, and wait for every unit time. When an agent takes an action, it needs to update its state. At this time, the state can be updated based on the delivery task, AGV, and cells. Respectively, the number of completed tasks, the state of the AGV, and whether the cell was occupied were defined in this way. Rewards are calculated based on the updated state to train the model as desired. We chose complete delivery task on time, higher AGV utilization, and decreased distance to destination as positive reward, and delayed delivery task as negative reward. The proposed model was verified with a simple code, and the AGV arrives at the destination as shown in the movie clip on the right. We will continue to conduct this research with the following plans. First, we need to validate our model and architecture beyond a simulation environment. Second, multiple AGVs and the combination with different type of logistic facilities such as forklifts will be considered. Third, using a real-time location system, it will enhance the dynamic obstacles data. The last, we will consider the impact of our application for the sustainability point of view. Thank you for listening, and if you want to know more about our interesting research topics and result, please find more detail about us in our website and our YouTube channel. I want to finish our presentation with some questions to the audience to get some more active feedback. If you have any comments on our future research, or if you have any expectation from reinforcement learning in your field, feel free to share with us. Thank you.